we're going to review some stuff from Unit 4 for our upcoming test. Feel free to skip through this video and find questions that you want to look at. And yeah, let's get started. So number 1, simplify the following. The square root of -72. Over in the side here, I just wrote that I equals the square root of -1, and basically all this definition is telling us is whenever we have a square root under the radical, we can substitute that negative for an I. And that allows us to take the square root of negative numbers, whereas before we weren't able to, but now that we have this little definition of our imaginary numbers, or I, we can. So first we just take care of that negative. Let's pop it outside. We have I square root of 72. So now we're going to simplify rad 72. The way that we simplify radicals is we look for the biggest perfect square that fits inside of our number. So I went ahead and started dividing 72 by perfect squares. 72 divided by 1 is 72. Obviously, 1 is not the biggest perfect square that we can fit into 72 because we divide it by 1, we get 72, and 72 can be broken down more. Then I divided 72 4 goes into 72 evenly, however, we get 18, and if we look at 18, we could fit a perfect square into 18. We could fit 9 into 18. So that's how we know that 4 isn't the biggest perfect square, and it's because the number we get after we divide, we can simplify it with another perfect square. So then I 72 divided by 36 gives us 2. And 36 is the biggest perfect square we can fit into 72. And we know that because the number we get after we divide can't be broken down anymore by perfect squares. So rad 36 times rad 2 would give us rad 72. Rad 36 is just 6. Rad 2 stays rad 2 because you can't pull out anything as perfect squares from 2. So our final answer is 6I. Simplify the following powers of I. So we have I to the 87. When we first started looking at powers of I, we saw that they follow a pattern. They go from 1 to I to -1 to -I, back up to 1 to I to -1 to -I to 1, on and on and on and on. So we can use this pattern to help us simplify large powers of I into smaller powers of I that we know the values of. I showed you a way to do this on your calculator using A plus BI mode, but you can't simplify higher powers of I in your calculator. So something like I to the 87 or I to the 90 or I to the 2019. You can't plug into your calculator, it won't work. You'll get a really weird number. However, you can use your calculator to help you remember your I to the 0, I to the 1, I to the 2, I to the 3, and then I to the 4. So those are values that you can just plug in and get the answer. So to simplify this, I want to know how many groups of 4 fit into 87. So I do 87 divided by 4, and I get that 21 groups of 4 fit into 87, and then I have 0.75 left over. And the reason why I'm interested in groups of 4 is because I to the 4 is 1. So I kind of want to group these up in 4s to see how many 1s I can get. So I to the 4, I can fit 21 here. This is going to always be 1 because I to the 4 is 1. 1 to any power is 1. Now I have to deal with my remainder. So 0.75 is the same as 3 over 4. So that means I need to add 3 more additional i's to get me to 87. To check yourself, your exponents should equal 87. So 4 times 21 is 84 plus my additional 3 that I have on the end that I got from my 0.75 brings us to 87. So we know that we split it up right. Out of the fourth is just 1, and we can get 21 groups of those, so that's why it's written like that. And then out of the third simplifies to negative I. So out of the 87 is equivalent to negative I. So when we are doing operations with complex numbers, I said to kind of treat them like polynomials and pretend the i's are x's. So we add and subtract complex numbers just like we add and subtract polynomials. We use our column method, which basically means just line up all the like terms. But before we can set up our column method, we just need to distribute our negative because we're subtracting. So negative, my negative is going to get distributed to my 2, and then to my negative 10i. So we would have 8 plus 5i minus 2 plus 10i. And now we can set up our column method. We have 8 plus 5i minus 2 plus 10i. And then we just combine, just like we would if this was 8 plus 5x and negative 2 plus 10x. We treat them like x's. 8 minus 2 is 6. 5i plus 10i is 15i. And that's your answer. There is a way to do this in your calculator. You would put it into a plus bi mode and then plug it in using parentheses around both complex numbers. So now we're going to multiply complex numbers. When we're multiplying complex numbers, we multiply them just like polynomials. You can pretend that your i's are variables, and we just multiply through as if we were multiplying polynomials together. For these, when they have mixed operations in them, you're going to want to follow PEMDAS. And I know that's a throwback to 6th grade, but it's important. So first, it's parentheses. I don't see any parentheses that we can take care of. I don't see any like terms we can combine within the parentheses, so we can just put a check over that. The next thing is exponents. I see one thing being raised to an exponent. That's my 3i squared. So my squared is going to jump to my 3 and my I. So this turns into 6i times 3 squared is 9. I squared is I squared times x plus I. I know that you can simplify I squared to negative 1. However, I would say leave your powers of I until the end and simplify them at the end. So we can keep just treating them like polynomials, multiplying and adding exponents where we need to, and then we can take care of the simplification at the end. So we took care of our exponent, and now we're going to multiply. We're going to multiply from left to right. So 6i times 9i squared, 6 times 9 would give me 54. I times I squared would give me an I cubed. You multiply this just like you would multiply 6x times 9x squared. So 54 I cubed times x plus I. So now you can do this one of two ways. You could either distribute your 54 I cubed to your x and then to your I, or you can use the box method. I'm going to use the box method because we just learned that with polynomials, and I feel it keeps things organized and in order. So 54i cubed goes on the side, x, and I. 54i cubed times x, that's just 54x I cubed. 54i cubed times I, well, I cubed times I would give me I to the 4th. So we have 54xi cubed plus 54i to the 4th. Took care of a multiplication. There's no division. There's no addition. This addition right here, we can't combine because they're not like terms. In order for us to be able to combine them, they would have to have matching I exponents, so I cubed and I cubed, and they'd also have to both have x's. And there's no subtraction. So we're done. We're at the end. However, I cubed is equivalent to negative I, and I to the fourth is equivalent to 1. So let's just simplify those powers of i's, and then we're done. So 54x times I cubed is negative I, plus 54 I to the fourth is just 1. So it goes negative 54 xi plus 54. This is not an a plus bi form, so all I'm going to do is just put it in a plus bi form. So our real part goes in the front, and our imaginary part, or the term with the I, goes in the back. So our answer is 54 minus 54xi. So we have 2x minus I minus 2x minus I times 2x plus 3i. So we have a couple of mixed operations. We have some multiplication, we have some subtraction. So I think the best way to approach this would be to use PEMDAS. So first, let's look for our parentheses. There's nothing inside these parentheses that we can combine because there's no like terms. So we're good. There are no exponents to take care of. So we're good there. First, let's look at multiplication. We have 2x minus I times 2x plus 3i. So we can multiply those together. You could do this one of two ways. You could just distribute each term, or you can use the box method. I'm going to use the box method because that's the way we learned it for polynomials, and multiplying complex number mirrors multiplying polynomials, so I think it would just be a good way to show it. So 2x times 2x is 4x squared. 2x times negative I is negative 2xi. 2x times 3i is 6xi. 3i times negative I is negative 3i squared. Our diagonals combine. So we get 4x squared plus 4xi minus 3i squared. Now this is not an a plus bi form, and we know that I squared equals negative 1. So we get 4x squared plus 4xi minus 3 times negative 1. So 4x squared plus 4xi plus 3. 3 is a real number, and 4x squared is also a real number because there's no I in it, and an x is just some number. So our real component would be 4x squared plus 3, and our imaginary component, I'm just going to put parentheses around my real component, would be 4xi. All right, so now our equation looks like this. 2x minus I minus 4x squared plus 3 plus 4xi. So I took care of multiplication. There's no division, there's no addition, but we have subtraction. To subtract complex numbers, we use our column method. However, first we need to distribute our negative. So negative to the 4x squared, negative to the 3, and a negative to the 4xi. So we are left with 2x minus I minus 4x squared minus 3 minus 4xi. There are no like terms here to combine at all, and we have no powers of I to simplify. So there's nothing really else left to do with this problem except put it in a plus bi form. Now it looks a little strange. So to start putting it in a plus bi form, we're going to gather all the terms that don't have an I. So 2x is a real term because there's no I. Negative 4x squared is a real term because there's no I. And negative 3 is also a real term because there's no I. So 2x minus 4x squared minus 3 is going to be our real component. Because if we had a value of x, this would just be some real number. And there's no i's attached to it, so it's not imaginary. And now we're just going to combine our imaginary components. So negative I is imaginary, and negative 4xi is imaginary. My imaginary component, they all share an I. So I'm just going to factor that I out. So our answer turns into 2x minus 4x squared minus 3, which is just some real number because there's no i's in there, so that's our real component, plus negative 1 minus 4x times I. So all I did was just take out that I. So this, because it's attached to our I, is our imaginary component. I know that's not how you normally see a plus bi form, but it is a complex number and it is an a plus bi form. It just looks a little different because we have that x in there. So the complex conjugate will always have the form. If I'm given a complex number that has a plus bi, the complex conjugate will always be an equal real part and an opposite sign imaginary part. And when we multiply complex conjugates together, we're going to get a number that's purely real. So all that means is that we're not going to have i's in our answer. If you're multiplying complex conjugates and you end up with an I in your answer, you did something wrong, and you should go back and check it or plug it into your calculator and check it. So the conjugate to 3 plus 4i would be an equal real part, which is 3, and an opposite sign imaginary part, which is negative 4i. So we're going to multiply together 3 plus 4i and 3 minus 4i. You could distribute this, double distribute, or use your box method. I'm going to use the box method because multiplying complex numbers together kind of models multiplying polynomials together, and this is the method we used for multiplying polynomials together. When you're working with complex numbers, you can treat them kind of as polynomials. You can pretend that the I is like a variable, but at the end you just have to remember to simplify your powers of I because they do have exact values. So 3 times 3 gives me 9, 3 times 4, I gives me 12, I, 3 times negative 4i gives me negative 12, I, negative 4i times negative 4i times 4i is negative 16i squared. Our diagonals combine, so we get 9, 12i minus 12i, those cancel out, and we're left with negative 16i squared. Now, this is not a purely real number because we have our I here. And this also isn't an a plus bi form, so we know we still have some work to do. I squared is equal to negative 1. So this turns into 9 minus 16 times negative 1. 9 plus 16, which is 25. And that is our answer. 25 is a purely real number, so we know we did it right. And that's it. Use the discriminant to describe the roots of the following quadratic equation. So we have 2x squared minus 8x minus 4. Whenever it says describe the nature of the roots or explain the roots, you're going to probably be using the discriminant. The discriminant is b squared minus 4ac. It's the number under the radical in the quadratic formula, and it just tells us how our roots are behaving, and it gives us some kind of information on our roots. To do these questions, you need to memorize the chart. The chart is on the front of our jigsaw activity that we did last week. It's also on homework, and it's also on your pink page, on your topic review page. So those cases are everywhere, so it's super important that you know them because that's how you answer these questions. So to figure out how our roots are, we have to look at our discriminant. So let's just plug into our discriminant. Negative 8 squared minus 4 times a, which is 2, times c, which is negative 4. Plug that into your calculator and see what you get. So after you plug that into your calculator, you get that it equals 96. 96 is positive, so it's greater than 0. And 96 is a non-perfect square. So what we can determine from this is when our discriminant is positive in a non-perfect square, or the number under the radical in the quadratic equation is positive, our roots are going to be real. If it's a non-perfect square under a radical, their roots are going to be irrational. So that means when you take the square root of a non-perfect square, you get some kind of long, ugly, non-repeating decimal. We call these irrational numbers. So if our discriminant is irrational, or if the number under the radical will be irrational, then our roots are going to be irrational. And they're also unequal. And all that means is you're going to get two distinct roots, and it's going to hit the x-axis twice. Real quick, the other cases are when our discriminant, b squared minus 4ac, is less than 0, our roots are imaginary, and that's when you get a negative number under the radical, so obviously you get imaginary numbers. B squared minus 4ac is equal to 0, our roots are real and equal, and then when b squared minus 4ac is greater than 0, and it's a perfect square, our roots are real, rational, unequal. X squared minus 2x plus k, what values of k will generate imaginary roots? So now we're going to use what we know about the discriminant to find this value of k that will make a quadratic equation that has imaginary roots. So when we have imaginary roots, we know that our discriminant, so b squared minus 4ac, has to be less than 0, because the discriminant is the number under the radical of the quadratic equation, quadratic formula, and when the number under the radical is negative, it's an imaginary number. So let's just plug in what we have. We have that b is negative 2, so negative 2 squared minus 4 times a is 3, and c is the value that we're trying to find. So I'm just going to plug in k, less than 0. 4, so negative 2 squared is 4, minus 4 times 3 is 12, k is less than 0. I'm going to move the 4 over, so right now we're just trying to solve for k. I'm going to get negative 12, k is less than negative 4. I'm multiplying negative 12 by k, so to undo it, I'm going to divide by negative 12. So divide both sides by negative 12, and we get k is greater than, and the reason why I flip my sign is because I'm dividing by a negative. Whenever you divide by a negative with an inequality, you have to flip your sign over. So if it's less than, you flip it to greater than. If it's greater than, flip it to less than. Super important, don't forget that. So we get k is greater than 1 over 3. So any value bigger than 1 over 3, so 1, 2, a million, any value of k that's greater than 1 over 3 will make this quadratic have imaginary roots. Find the roots of the following quadratic equation. State your answer in simplest a plus bi form. So this a plus bi form here is kind of giving us a hint that when we solve for our roots, they're going to be complex or imaginary. However, solving quadratics that end up in complex roots is no different than solving normal quadratic equations. You're still going to use the same methods. You can still use quadratic formula. You can still factor. You can still complete the square if you want to. The only difference is going to be at the end, when we take the square root, we're going to end up with something with an I instead of just a real number. So I'm going to use quadratic formula because that's something that will always work for any quadratic no matter what. And I'm going to just get it into standard form. So x squared, I'm going to move my 6x over, minus 6x plus 12 equals 0. And now I'm just going to plug into my quadratic formula. So x equals negative -6 plus or minus -6 squared minus 4 times 1 times 12 over 2 times 1. So whenever we're doing the quadratic formula, I always tell you guys to attack what's inside the radical first. So let's just plug in -6 squared minus 4 times 1 times 2. So after we plug in those numbers under the radical into our calculator, we get that x equals 6. I just multiplied the two negatives together to get me a positive 6. Plus or minus radical -12 over 2. So now I kind of want to deal with this radical. Since I have a negative under it, we kind of can't really put it into our calculator and get a decimal and call it a day. We need to simplify that radical. So I'm just going to take it off to the side because I think it's just a little easier to look at. So whenever we have a negative under the radical, our first step is to pop it out and make that I. So we get I rad 12. And now we need to think about the biggest perfect square I could fit into 12. So 12 divided by 1 gives me 12. I don't think that's simplified enough, so I'm going to move on. 12 divided by 4 gives me 3. So rad 4 times rad 3 would give me rad 12. So, and since 3 can't be simplified anymore with any perfect squares, we know that 4 is the biggest perfect square that fits into rad 12. Rad 4 is 2. Rad 3 stays rad 3. So negative rad 12 simplified is 2i rad 3. So I'm just going to go ahead and write that back up here. So x equals 6 plus or minus 2i rad 3 over 2. The question asks for our roots in simplest radical form. And this isn't simplest radical form. And the reason is because 6 and 2 share a factor of 2. So I'm just going to write a 2 above 6 and a 2 on 2. 2 and 2 also share a factor of 2. Since my three numbers, my three coefficients here, have the same factors, make like a little triangle, if they all have the same factors, we can divide out that factor. So 6 divided by 2 is 3, plus or minus 2 divided by 2 is just 1i rad 13. 2 divided by 2 is 1, so our root is 3 plus or minus i rad 3, not 13. In the following parabolic equation, find the vertex, value, p, focus, and directrix. So when we're dealing with this, I told you guys there's a way to write the equation where it's easier to pull out values. So the form that I want you to look at this equation whenever we're pulling out values of like the vertex, the value of p, the focus, and the directrix is I want you to use the y minus k form, not the y equals form. The y equals form is really good for graphing or on multiple choice. Usually the formulas will be in y equals form. However, when we're like manipulating and trying to figure out what the vertex and the focus is, I want you guys to use the y minus k. So obviously this is in y equals, so we just need to move it into y minus k. So I'm just going to minus my 3 over to get it to look like this form. So we have y minus 3 equals 1 over 4 x minus 4 squared. So now we have it in the right form. We can start pulling out values. Our vertex will be h comma k. Y minus 3 is y minus k. X minus h is x minus 4 is x minus h. Whenever we're pulling out the vertex of our parabola from this form, you pull out the number and you switch the sign. So it's y minus k, so our k is going to be 3. Another way that you can think about that is you can just solve for y. So you would add 3 to both sides, and y would equal 3, so our k would equal 3. Same thing with x. Our x would equal 4. If you want to do that, that's fine, but you can also just think about it as flipping the sign. So if you have a minus 3 in the equation, your value would be plus 3. If you have a minus 4 in the equation, your value would be plus 4. So my vertex is 4, 3. One common mistake that I see everybody make is they flop the values of k. They think that k is with the y and h is with the x because the y comes first, so you just automatically write that down in the h spot. However, just try to remember that our h value is with our x and our k value is with our y. All right, so let's find our value of p. So in my original form, I have 1 minus 4p. And in my parabolic equation, 1 over 4p is equal to 1 over 4. So basically, I just looked and saw what fraction is in that spot, the same spot as this guy, and set them equal to each other because they're equal. And then you can just cross multiply. So 4p equals 4, so p equals 1. So the distance between the vertex and the focus, or the vertex and the directrix, is 1. Now let's look and find our focus. Our focus is the point that's equidistant, and the directrix is the line that's equidistant. So since our focus is a point, we're going to have an x value of h and a y value of k plus p. So our h is 4, and our k is 3, and our p is 1. So our focus is at 4, 3 plus 1, or 4, 4. And our last important point is our directrix. Our directrix is the given line. So a parabola is formed by the points that are equidistant from our given point, which was our focus, and our given line, which is our directrix. So since it's a line, we're going to have it in y equals, and it's going to be y equals k minus p. So y equals 3 minus 1, y equals 2. So our directrix is at y equals 2. Just a couple notes. If our p is positive, that means our parabola is going to open upwards, like a smiley face, and our focus is going to sit inside of our cup or our smiley face. If the value of p is negative, it's going to open downwards, it's going to be a frowny face, and our focus is going to be inside the mountain. Our directrix, we can think of it as an electric fence. Our parabola points away from it, so it kind of runs away from the directrix. It never touches it. Use the given information, form an equation of a parabola. So I'm just going to write down our form that we follow. Y minus k equals 1 over 4p, x minus h squared, or the y equals form, which would be 1 over 4p x minus h squared plus k. So whenever they give you information, they ask for an equation. I think the best way to attack these is to draw a picture using our given information. So I'm just going to draw a quick little sketch. Our focus is at the point 3, -3. And our directrix is at the point as a line, which is y equals -5. So this isn't enough information to form an equation. We need h and we need k. And we know that h and k are our vertex. We also need p. But we can't get p until we have our vertex. So I think the best move right now would be to find our vertex. The vertex sits right in the middle of our directrix and our focus. So since our directrix and our focus are 4 units away from each other, our vertex has to be 2 units away. So my vertex would our focus and our directrix are 2 units away from each other, so my directrix is at 3, -3, and my directrix is at y equals -5, so that's 2 units. So since my focus and my directrix are 2 units away, my vertex has to sit right in the middle, so that means my vertex can only be 1 unit away from both of them. So my vertex should be at 3, -4. And now that we have the location of our vertex, we can get our value of p. So p is the distance from the vertex to the focus, and it is 1. Now, the reason that I know it's positive is because my directrix is below my vertex, and my parabola will never hit my directrix. So if my parabola was facing downwards, or if I had a negative value of p, I would hit my directrix. So we know it can't be negative. Also, if my parabola was downwards, my focus wouldn't sit inside of it. And we know that our focus has to sit inside of our parabola. So, from those two little known facts, we can gather that our value of p is positive 1 and not negative 1. So now we have enough information, so we can just start plugging into our equation. So y minus k, we have k is negative 4, so y minus 4 equals 1 over 4p. Well, we have p, it's just 1, so we plug that in, times x minus 3 squared. So it's y plus 4 equals 1 over 4 x minus 3 squared. You can leave it like this, or you could write it in the y equals form. So all you would do is just subtract this 4 over, and you would get y equals 1 over 4 x minus 3 squared minus 4. And that would be the equation of your line with a focus of 3, negative